Hello friends, so today we are going to solve the questions from the chapter magnetic fields, and so the first question we are given. Suppose that the current I2 in figure B is equal to I1 but reversed, so that CD is repelled by GH. Suppose also that AB and EF lie vertically above GH and that the length BC and CD are 30 and 15 centimeter respectively, and that conductor BCDE, which is 1 millimeter distance copper wire, is as figure A. Okay, later on I'll draw the figures, both A and B, has a weight of 0.08 Newton per meter. In the equilibrium, the deflection of the hanging frame from the vertical is such that the R is 0.5 centimeter. How large is the current? So we have to find the value of the current under the equilibrium condition, and it states that second part is the equilibrium stable? So let me first of all draw the figure, and so we are given that we have two conductors basically, and these two conductors are in two different configuration. Okay, so it is given in part A as well as part B, and one second. Okay, so let me draw the important figure, that is figure B. Figure E is just a representation of figure B. Okay, so in figure B we are given that we are having a, suppose this is our basic axis, and in this axis we are having a frame, and here it is a hanging frame. So this is the hanging frame, and it is given as our B, C, D and E. Okay. And along with that we are also having a GH conductor. Okay. And suppose this is our GH conductor. So this is G and this is our H, and the direction of the current in both is such that it is opposite direction. Okay, so let us assume that the direction of the current in GH is in this direction, and let us call this as our I1, and CD is in this direction, and let us call this as our I2. Okay. And so because of the repulsion between this GH and CD, so if I look from the side I can just draw it. It will be like this. So this is our point B, and because of the repulsion, our BC will be making the angle of, suppose, theta with the vertical. So this is my C, and let us call this vertical as my C prime. And this distance is given to us as our R, and value is known to us, given to us rather. So, and the value of the current is given that I1 and I2 are equal. So we have to find out this value of the current, and the respective lengths are given to us as our BC, as also our CD, that are given to us. Okay, 1 second. Okay. So the various things that are given to us. So first of all, we are given that our BC and the vertical sides of the frame, so we can say we are having the vertical sides, and these vertical sides are our BC and our DE, and their length is given to 30 centimeter. So we can write this as 0.30 meters. And we are having a bottom side, that is CD. Bottom side is given as 15 centimeter, so that will be 0.15 meters. And from this point B and E, this is like a hinge, so this CD can move back and forth. So it means our BC, it can move like this, and because of the repulsion, so we can write that it will be moving only in one direction, that is away from the wire, okay, because of the force of the repulsion. And this repulsion will be because of this GH. Okay, if you look from the side, we can say this, our G will be somewhere here. Okay, so it's because of the current flowing and this wire GH, there will be a force of repulsion. So we can assume that with respect to the vertical, it's making an angle of theta. Therefore, we can write a total moving wire. We can say total moving wire will be our BCDE. Therefore, its length is, suppose, of L total, and that L total will be our BC plus CD plus DE. So this will be 0.30 plus 0.15 plus 0.30, which comes as our 0.75 meters. And we are also given that it has a weight of 0.08 Newton per meter. So we can say weight per unit length. Weight per unit length. Let us call this as W, and that is our 0.08 Newton per meter. And the deflection, which is nothing but R, okay, so this will be our R with respect to vertical. And the deflection of the hemming frame from the vertical. Deflection of hanging frame from vertical, which is our R, and this R is 0.5 centimeter, or we can say 0.005 meters. Okay. And so it means that the distance between the CD and our GH, this is our R. And so the direction of the current is our, you can say, opposite. I1 is flowing in, suppose, towards the right, so I2 will be in the left direction. Okay, so I1 we have taken in the left, so I2 will be flowing toward the right side. Okay, direction of the current is opposite. So first of all, we are going to find out what will be the center of mass of this frame BCDE. Okay. So we are going to find out center of mass of BCDE, because there will be two forces. One force will be force of repulsion, that is going to produce a torque, and another force will be the weight, because it is aligned at an angle of theta. So the weight will be vertical downwards, so it is going to produce its own torque. Another one will be the force of repulsion, that is also going to produce a torque about this point B. Okay. So we are having two forces, so obviously there will be two torque. And first of all, we are going to find out center of mass, and that is going to help us to solve this forces. Okay. And for that, let me redraw the figure. So this is our point B, and this is our E, this is C, and this is our D. Okay. And in this case, we assume that this BE is a representation of axis, that is, Z is equal to 0. Okay. So everything will be for Z less than 0. For all the values, that will be Z less than. Okay. And so we have two vertical sides, BC and our DE. Okay. So therefore we can write that for each vertical side, for each vertical side, BC and DE, we can write that its mass, and for the sake of convenience, let us introduce a unit mass, that is m, and we can easily calculate it based on this unit mass. Okay. And we also know that the total length of the wire, that is our BCDE, is our 0.75. Okay. So let us consider a unit mass which is our m. Okay. Therefore, for each vertical side, which is our BC and DE, we can write its mass, that is a mass for our vertical will be equal to our 0.30 and 0.15 and multiply by our m, and which gives us that mass of our vertical will be equal to 2 times m, and our bottom side CD let us call this as mass as our m bottom, which will be equal to our CD is having a length of our 0.5, so this mass will be our m. Thus the total mass will be equal to, let us call this a capital M, and this is our 2m plus 2m plus m, which comes as our 5 times m. So we got the mass of this entire section, that is our B, C, D, E. And we have to remember we calculated it based on we took a hypothetical mass, unit mass, that is m. Much more easier to find out our center of mass. Okay. And now let us find out the center of mass of each side. Okay. So for our BC, let us assume that it is having a center of mass somewhere here, and we denote this as ZBC. And for CD, let us suppose the center of mass is somewhere here, and we denote it as ZCD. And for DE, it is somewhere here, and we denote it as ZDE. Okay. Therefore, because we know for this vertical side BC, the center of mass will be at the half unit length, half of its length. So it means BC is ZBC will be nothing but the midpoint of this our side BC. Similarly, for our DE, this center of mass will be at the midpoint of this side, and similarly for this. Therefore, we can write that our center of BC so we can say that our center of mass of our BC, which we called as ZBC, will be our at 15 centimeter, or in terms of mass we can write this as 0.15 meter. Okay. And similarly we can write for our ZDE of our DE, which is our ZDE. Once again it will be our 15 centimeter. Okay. And for our this CD is of our CD, which is our ZCD, because CD is our 15 centimeter long, and both C and D are 30 centimeter below from the top. Therefore, we can say that CD will be equal to 0.30 meters. Okay, and we can write this also 0.15 meters. Now we can easily calculate the center of mass this entire frame. So you can this the center of mass of our the frame, which is our BCDE, will be equal to the total mass of the entire frame, which is our 5m, and then we come to our respectively, that is our twice m multiplied by its ZBC plus twice m multiplied by ZDE plus m multiplied by ZCD. So we substitute the value, we get that our Z of our center of mass, and we can easily cancel out our m, and this will be coming as our 5, so this will be 15 plus twice of 15 plus 1 times 30, and this will be giving us as 0.18 meters. So it means the center of mass from the top line will be our at 0.18 somewhere here approximately. So this will be our Z center of mass. And the total length we already know, that is our 0.75 meter. Therefore we can write that our total weight of BCDE that is our capital W will be equal to weight per unit length, that is small w, and our total length, that is our LT, and this comes as our 0.08 multiplied by 0.75. So we get that the total weight of BCDE will be equal to 0.06 Newton. Okay. So basically this weight is nothing but the force of gravitation that will be acting in the downward direction at the center of mass. So we can say this is gravitational force acting downward at center of mass. Now let's find out what will be the various deflection as well as the torque. Okay. And like we said that this was our point B, this is the vertical, and with respect to vertical, this our BC is making an angle of theta, and let us call this as C prime, and the distance between this is given as our R. Therefore, for a small angle theta, we can write that our tangent of theta is approximately equal to our sine of theta. And so we can say geometry of a deflection and torque arms. Deflection and torque arms. So we can say for small angle theta, we can write that our tangent of theta is approximately equal to sine of theta, and that will be R upon our BC, and therefore we can write R is our 0.5, BC is our 30. Okay. So we can sort it out later on, that's not a big problem. And because of this, okay, now obviously there will be a force of repulsion like we said it here. Yeah, so there is a force of repulsion, okay, and between the wire GH as well as CD, okay. So because this force of repulsion, this is nothing but angle of theta. Okay. So we can say that the magnetic force on CD, let us assume this is given as our F. And so for our small angle theta, we can assume that our BC is nothing but equal to our BC prime. Okay. For small angle theta, from here also we can say that our BC is equal to our BC prime, and therefore it will be equal to our 0.03. So BC is nothing but a vertical, and this BC prime is vertical, and BC is at an angle of theta with respect to this BC prime. But for small angle theta, their length is almost equal. Okay. And so the magnetic force is F, and the perpendicular distance is our BC prime, okay, which is equal to our BC. Therefore, we can write that the torque magnitude, its torque magnitude will be equal to F and multiply by our perpendicular distance, that is our BC prime. And later on we can just substitute the value. And we are having a mass W, and that is acting in the downward direction at the center of mass. Okay. So our this PC, if you look from side, so this will be our weight W. And we know that because initially the frame was entirely vertical. Okay, so let me redraw it. So initially our frame was vertical, so this was somewhere here, our weight, that is our W, and its distance we already know, that is given to us as our 0.18. Okay, because of force of repulsion, this point will be somewhere here, so we are going to get this weight somewhere here. And so if we, let us call this as our this is our P, and this is our P prime, and this is P. So for small angle theta, we can say that our BP is equal to our BP prime, which will be equal to our 0.18. And so we can say that the weight W acts at the center of mass, and this is at a distance of BP prime, okay, at vertical distance, which is our BP prime, and this is our 0.18 meters. But for small angle theta, we can write that our BP prime is equal to our BP, which is our 0.18 meters. Therefore, we can say that the torque due to weight, let us call this our tau g, will be equal to our W, and this comes as our B. Let me call this as our dW. So this comes as a dW sine of theta. Okay. And under equilibrium condition, the torque because of this weight will be equal to torque because of the magnetic force. These should be equal. Therefore, we can say that at equilibrium, torque because of the weight should be equal to torque because of our magnetic force. So we can write our F times 0.30 will be equal to our W times 0.18 sine of theta. And we already know the value of sine of theta is our 0.5 divided by 30. Okay. Therefore, we can substitute it, and weight also we know W capital is our 0.06 newtons. Okay, so let us substitute it. So we get our F is equal to 0.06 multiplied by 0.18 times this is 0.30, and sine of theta is our 0.005 upon 0.30. So we get the value of the force, that is F, is equal to our approximately will be equal to 6 into 10 to the power minus 4 newtons. Okay, so this is the force, a force of repulsion between the two wires, that was our F. And in this case, so in this case we have to remember that we were having two wires. One wire is our GH, okay, and another wire is in the form of a frame, that is our BCDE, and the point B and E, they are like a hinge. Okay, so this CD, if we look from our side view, so this is our point B and this is C, and the vertical is our BC prime. So angle of deflection between the vertical and this BC because of the force of repulsion between this GH and CD is taken as our theta, and the distance between the two is our R. And we have to find out the magnitude of the current that is flowing in, and it is also given that value of I1 is equal to our I2, which we are going to say, let us suppose that is our I, and we have to find out this value of I. And for this value of I, we already found out what will be the value of the force, that is a force of repulsion, because under equilibrium there will be only two forces acting on it, the force of repulsion and the weight that will be acting in the downward direction. So both are going to produce a torque that will be in opposite direction, and it will be balanced by them. And in this case we have to assume that the angle of theta is very small. So we got the value of our force. Now we can easily find out what will be our value of the current, okay? Because we know that if there are two parallel conductors, current flowing is I1 and I2, and let us suppose the distance between the two is our R0. So we already know the value of the force that will be acting between the two parallel conductors. So we already found out value of force, so we are going to use that the magnitude of force between two parallel conductors, and that force is F, which will be equal to over mu naught I1 I2 2 pi r naught, and the length is suppose given as our L. Okay, and in our case, the given question, we are given that value of I1 is equal to I2, suppose that is equal to I, whose value we are going to find out. Therefore, we can write that our F and our R naught in this case is given as R, whose value is known to us. We can substitute that later on. Okay. Let me write it. This is 0.005 meters. So we can write this is equal to over mu naught I square 2 pi R times, and the length is our, in case is our L total. Okay. And length is our, sorry, not L total, but the actual length on which the force is acting. L total is the total length. So the conductor is our CD. Okay, so we can say our length of section, our CD, and that length is our 0.15. Meters. So this is multiplied by our length of our portion CD, and therefore we can write that the value of force, we can say this will be equal to our, we can substitute value of mu naught, which is our 4 pi into 10 to the power minus 7 times our I square, length is our 0.15, and this comes as 2 point R is our 0.05, and value of force we already know is our 6 into 10 to the power minus 4. So this is the value of force that is known to us, and here we see pi, this 2 goes away, and I square. Okay, so we can just sort it out. This will be coming as our 6 into 10 to the power minus 6 I square is equal to 6 into 10 to the power minus 4. Therefore, we get that value of the current I will be equal to over 10 ampere. So this was our value of the current that will be flowing in the both the wires. Okay. And next it talks about the stability of the equilibrium, and stability of equilibrium, and we know that we are having two torques that are acting. First torque is because of our magnetic force, that is our tau B, and obviously that will depend on theta, so we can say F theta multiply the distance, that is our 0.3, and we are having because of our gravity, which is our W.18 and sine of theta. And we assume that, let us suppose at theta is equal to theta naught, this is the angle where the equilibrium is. Okay, so this is a condition for our equilibrium. Therefore, we can write that the magnetic torque at angle of theta naught should be equal to torque because of the weight at the angle of our theta naught. Okay, this is our condition of our equilibrium. And let us assume that angle which is slightly greater than our theta naught. You can say for our theta which is greater than our theta naught. So obviously we can from here clearly say that our separation between CD and GH increases. Separation between CD and GH increases. And we also know that the magnetic force, which is our f of theta, is inversely proportional to the distance between the two. So we can say the magnetic force which is our f of theta is inversely proportional to r of theta. Okay, r means the distance between the two. Okay. So it means as theta increases, our r of theta is also going to increase. So if our theta increases, from here we can say that our r of theta is also going to increase, or we can say that our f of theta is going to decrease. And if our f of theta is going to decrease, we can say that the torque because of magnetic field is also, it becomes smaller than its equilibrium value. Then its equilibrium value. And the second torque, which is our due to gravity, it increases. Okay, because for small angle theta, our sine of theta increases as theta is going to increase. So this gravitational torque increases. Therefore, we can write that for angle theta greater than the equilibrium angle, our gravitational torque is greater than our equilibrium gravitational torque. And which is nothing but our the magnetic equilibrium torque, which is greater than our torque at angle of theta. And so from here we can say that the net torque tends to rotate the frame back toward the smaller angle. The net torque tends to rotate the frame back to smaller value of our theta. And similarly, we can say if theta is less than theta naught, okay, it will be our back toward the theta naught. So it means in both the direction, it will try to come back to its equilibrium angle, that's our theta naught. Or in simpler terms, we can say that this is our BC, and somewhere here we are having the torque which is because of our gravity. Okay, I'm sorry, this is weight, not torque. Okay, so it's the weight because of the gravity, and this is the equilibrium angle of a theta naught, and there will be a force, okay, and that will be because of our magnetic field. So if the value of this becomes greater than the equilibrium angle, the value of this torque because of the weight is going to increase. So its weight is going to increase, so it will try to move back to its original equilibrium angle is our theta naught. That's the basic meaning of that. Therefore, we can say it is nothing but our a stable equilibrium. Okay. So both cases, it has a tendency to come back to its equilibrium position. Its reverse is also true. If the angle is, suppose this is angle theta, so it is obviously less than our equilibrium angle. So the torque, it will be net torque, will be the magnetic force obviously going to increase. Okay, so magnetic force is going to move this wire towards once again our theta naught. Okay, so one time a magnetic force is going to dominate, and the other time our weight is going to dominate. Weight means the torque because of their respective forces is going to dominate. Next question. Consider two circular rings of copper wire. One ring is scaled up version of the other, twice as large in all regards, radius, cross-sectional radius. If the currents around the rings are driven by equal voltage source, how do magnetic fields at the center compares? So we have to find out, make a comparison between the magnetic field at the center when one ring is the scaled version of the other, okay, and they are driven by the same voltage sources. Okay. So let us start with our smaller ring. So you can say for our small ring, and for that let us consider that we are having a radius which is a capital R, and the cross-sectional radius is supposed as our small a, and the resistivity is supposed is our rho. Therefore, from here we can write the length of the wire, that is L will be equal to the circumference, that is our 2 pi r, and cross-sectional area that is a capital A will be equal to pi a square. Therefore, we can say its resistance, and let us suppose this called as R small, will be equal to rho L upon A, and this comes as rho 2 pi r and pi a square. So we get our R small will be equal to our rho, and here pi and pi cancel out, so this comes as twice r times a square. So this is the resistance of our small. Okay. And it is given that the large ring is the scaled up twice in all regards. So we can say our large ring is scaled twice. Therefore, can write that its radius, which is r prime, will be equal to twice r, cross sectional radius, which is a prime, is equal to twice a. Therefore its length, which is L prime, will be equal to 2 pi r prime and giving us 4 pi r, and cross sectional area a prime will be equal to pi a prime square, and this comes as our 4 pi a square. Therefore its resistance, which we can say resistance large, will be equal to our rho L prime a prime, and this comes as rho, and this is our 4 pi r divided by 4 pi a square, which giving us that our rho r upon a square, or we can say that our resistance of our large will be equal to 1 by 2 resistance of our small. So we got the relationship between the resistance of our smaller as well as our large, and we are given that it is both are being driven by the same voltage. So we are given that each ring is connected to same voltage. Let us suppose that is our V. Therefore we can write that the current in our small will be equal to V upon resistance of our small, and current in the large will be equal to voltage and resistance of our large. And we already know that the resistance of large is 1/2 of our resistance of a small. So we can say this is equal to V upon resistance of our small divided by 2. Therefore we can say that our current in our small, not current in the small, but current in the large. So we can say current in our large will be equal to twice current in our small. So we got the relationship between the value of the current that will be flowing respectively in each ring. And now we can use the standard formula for magnetic field at the center of a circular loop. You can say our magnetic field at the center of circular loop, and that is our B, which is our mu naught I upon 2 times R. So we can divide this into respectively small as well as big. Therefore we can say magnetic field in our small will be equal to our mu naught, and this comes as I small, and divided by 2R. And magnetic field in our large is equal to over mu naught I large upon 2r prime, and we can substitute value of our I large is twice of this, so we can write this as mu naught twice current I of small, and our r prime is our 2 times twice of our r. Okay. And so here 2 and 2 cancels out, therefore we get the magnetic field of our large is equal to mu naught I small divided by 2r, which is nothing but our magnetic field of our small. So this comes as magnetic field of our small. Okay. Therefore, we can write that magnetic field of our large is equal to magnetic field because of our small at the center. So the magnetic field in both the cases are equal. Okay. Next question. It states that two parallel rings have same axis and are separated by a small distance epsilon. They have the same radius a, they carry the same current I but in opposite direction. Consider the magnetic field at the points on the axis of the ring. The field is 0 midway between the rings because of the contribution from each of ring cancels, and the field is 0 very far away. So it must reach a maximum value at some point in between. Find this point. Work the approximation where epsilon is very much less than as compared to a. Okay. So which basically means that we are having two rings, and suppose, let me draw this figure approximately. Okay, so this is the common axis, and we are having, suppose this is the first ring and this is our second ring, and they are carrying same current but in opposite direction. So this is current I and this is a value of current I, and this is our coil 1 and let us suppose this is coil 2, and distance between them is given as our epsilon. Okay. And suppose somewhere here it is center, which is having a zero magnetic field. Okay. And so we can draw the graphical also with respect to, suppose these are the two centers, and so we already know this is the central axis, the first one, and this is the central axis of our second one. And if we draw our graphical representation of the magnetic field because of coil 1 as well as coil 2, obviously their direction will be in opposite direction, so we can just make an approximate for that. And so in the first case, the magnetic field will be something like this. And for other case also, it will be just opposite for that. So the magnetic field will be somewhere like this. And if we find out their net magnetic field, so the net magnetic field will be, but it will be coming something like this. This is not exact, but it will be approximately like this. So this is our magnetic field because of coil 1, only the magnitude part, and this is a magnetic field because of the coil 2, and this is, sorry, And one second. And this green one will be our net magnetic field. So we can just, and the direction will be something like this. So this will be B1 and this will be B2 approximately. So basically now we come to our original question. We have to find out, because it says that somewhere it is at the center is going to lie 0, and when at a far distance it will be infinity. So somewhere in between it will be maximum, and we have to find out that point. So distance between their respectively, this will be epsilon upon 2, and this distance will be also over epsilon upon 2. Okay, positive as well as negative. Okay. So let us write the equation, and we can say the field on the axis, magnetic field on the axis, magnetic field on the axis, and suppose that is our B, and at a certain point Z, which will be equal to over mu naught I a square and 2 a square plus z square and 3 by 2. Okay. And we are having 2 rings, so accordingly we can find out what will be the net value of our magnetic field. So we can say that for two rings, our magnetic field, it is Z will be equal to, this comes as a mu naught I a square, and this comes as 2, it will be over a square plus, it will be Z minus epsilon upon 2 whole square 3 by 2 minus, and because of a second, that is our mu naught I a square, and this will be 2, and it will be our a square plus z plus epsilon upon 2 whole square and 3 by 2. Okay. So it means the field is 0 when z will equal to 0. Okay, and it goes to 0 when z tends to infinity. Okay. So in between there will be certain value of maximum which we are interested in. Okay. But we have to keep in mind the value of epsilon is very much smaller than our a. Okay. So let us expand it for epsilon which is smaller than our a. So for our epsilon which is much smaller than our a, and we are only interested in this two functions, okay, because it is only containing our epsilon. So let us write it as our f of z, and our, we can combine this z function, epsilon function, as z is equal to z as our plus minus epsilon by 2. Okay, because one is containing minus, other one is containing as plus. Therefore we can write that our a function f of z will be equal to our mu naught I a square twice a square plus z square and 3 by 2. Therefore we can write that the magnetic field for a point at z will be equal to a function which will be z minus epsilon by 2 minus a function over z plus epsilon by 2. And for a small value of epsilon, we can just differentiate it and try to get the solution. So you can say for small epsilon, if we try to get the difference between these two values, that will be equal to our in the first order of epsilon. Okay. Therefore, we can write that the difference between these two will be equal to our minus epsilon, its first derivative, and our higher order function of our epsilon. Okay. And we can just ignore this part. Therefore, we can say that magnetic field Z will be approximately equal to minus epsilon f prime z. Okay. And let's find out what will be the value of our f prime. And f of z, we already know that our f of z is our mu naught I a square, and is 2a square plus z square 3 by 2. And our f prime z, we can take this as common by 2, and we are left with this will be minus 3 by 2 a square plus z square minus 5 by 2 and multiply by the derivative of our z square, that is 2z. And this gives us minus, and it will be our mu naught I a square, and this 2 cancel with this 2, and we are left with minus of 3, so this will be 3z and a square plus z square and 5 by 2. Therefore, we can say that our magnetic field will be approximately equal to, and so we get this as 3 epsilon mu naught I a square z divided by 2, I missed out. So this will be 2 a square plus z square 5 by 2. Now we have to find out the maximum value. Okay. And maximum value will be, because all the rest of the parameters constant, so it will be dependent upon only this function. Okay. So let us assume that our g of z is equal to our z upon a square plus z square and 5 by 2. So let me rewrite it. This will be z and a square plus z square minus 5 by 2. And let's find out its the derivative and equate equal to 0. So we can say our g prime z, and that will be equal to our, so we have to use, okay, this is our a square plus z square minus 5 by 2 plus z, and this will be minus 5 by 2 a square plus z square minus 7 by 2 times twice of z. And this gives us our a square minus 4z square times a square plus z square minus 7 by 2, and this will be equal to 0 because we have to maximize the magnetic field, that is this function which is our equivalent to 0, to find out the value. Therefore, because this is a positive function which cannot be equal to 0, we can say that only a square minus 4 z square is equal to 0. Therefore, we get the value of z is about plus minus a by 2. And therefore, this is our position where we are going to get a maximum value of our magnetic field. And we can also find out the maximum value of magnetic field. Okay. So we can say that our B max, and that will be at z is equal to a by 2. So with this will be equal to our 3 epsilon naught mu naught I a square divided by 2 times this comes as our a by 2 and a square plus a by 2 whole square and whole raised to power 3 by 2. So this will be coming approximately equal to as 24 epsilon mu naught I and 5 raised to power 5 by 2 a square. So this is the value of our maximum magnetic field. Next question. It states that a spherical shell with radius r and uniform surface charge density rho sigma spins with the angular frequency omega around its diameter. Find the magnetic field at the center. So we have a spherical shell and that is spinning. So we can just draw in the approximate figure for that. And suppose this is our shell and this is the axis of rotation which is also our diameter. So it is rotating along its diameter, and suppose this is center, and in this case we assume a small circular ring. So this is a small circular ring, and this ring is suppose having a length of over dl, and it is at a distance r radius and at an angle of theta. So because of this small ring, the magnetic field is suppose our dB, which will be in this direction. Okay. And so it's our length dl and its width it is given as dw. So like we said that we consider a narrow ring at theta and theta plus d theta. Okay, because this is narrow, so this small angle find the difference. Let me draw it here. So this is our ring, it is having a small thickness, something like this. So this angle is our theta, and the other angle is our, so this angle is our d theta. Okay, likewise. And from here we can also find out its radius. So this is our r, so this is going to our r sine of theta. And so consider a ring at theta and theta plus d theta centered at angle theta. Centered at angle theta. Therefore, we can say that the width of the ring let us call this as dw. This dw will be equal to r times d theta, and the radius will be equal to our r sine of theta. And first of all, we have to find out the magnetic field, and for that we are going to find out its area, then we come to the charge, and then we come to our current as well as the magnetic field. So we start from our charge and current of the ring. Charge and current of the ring. And so because this ring is length dl, width dw, and let us suppose the charge it is having is our dq. So we can say that area of the ring and that is our dA, and that will be our length of the ring multiplied by its width, and the length is nothing but its circumference, that is our 2 pi, and its radius, and times our dw. Okay, and the width is our r d theta. Therefore we can write that its area will be equal to 2 pi r square sine theta times d theta, and our charge on the ring, and let us suppose that is our dq, which is our charge density multiplied by our area, and we get that this charge dq will be equal to charge density, and area we already know is our 2 pi r square sine of theta and d theta. Okay. And it is rotating about the axis, so we can easily find out what will be the speed of the charges. Okay, and its angular velocity is given as omega, and at a polar angle of theta. Therefore your speed of charges and like we said, it is rotating about angular speed of omega, and the polar angle is given to us our theta. Therefore we can say that the distance to the rotation axis distance to rotation axis is nothing but our, suppose it is given as rho, and let us call this as our r naught, not as rho. So this is our r naught, which is nothing but our r sine of theta. So from here we can find out the linear speed, okay, or in this case it will be tangential. Okay. So we can say our linear or tangential speed, which is v, will be equal to omega times our r naught. Therefore we can say that our v is equal to our omega times r sine of theta. And now we are going to find out the current in the ring. And this ring is going to behave like a circular loop. Okay, so this is like a small loop, circular loop, which is having a charge dq, okay, and it is moving like a, you can say, around the z-axis. So this is our z-axis, and it is moving with the linear speed of our v. So we can say the ring behaves like a circular loop of charge dq, okay, all moving around z-axis with speed v. Therefore we can say that the time for one full revolution that is about t, will be equal to about 2 pi r naught divided by v, and this comes as our 2 pi r sine of theta, and v is our omega r sine of theta. So this comes as about 2 pi upon omega. Therefore we can write that the current di will be equal to our charge oblique time period, and this current charge dq is our charge density 2 pi r square sine of theta d theta, and this is our 2 pi upon omega. Therefore we get the value of the current di is equal to charge density omega r square sine of theta d theta. And now we come to the field at the center from one ring, okay, because we have drawn only one ring. So we can say that, and for that we can use our Biot-Savart law for a small element. That element we have is our dl. Okay. So we can say that field at the center from one ring. And like we said, the ring we are going to treat as a circular loop of radius r sine of theta carrying a current d of I. Okay. And for that, let me draw the figure again. So this is a sphere, and we considered a ring somewhere here, and it's the radius axis as well as diameter, and this radius is our r sine of theta, and we are finding out the magnetic field at the center of the sphere, okay, and which is nothing but the axis of the loop also. And this distance is our r and angle is our theta. Okay. So field at the center of the sphere from one ring, and for that we can use our Wyatt-Savitt's law for a small element. And that element is our dB will be equal to mu naught upon 4 pi divided by small current, small element, and our r square, and our direction, that is our r unit vector. And let us reformulate this Wyatt-Savitt's law according to our sphere. So we can easily see that at the center of the sphere, so our this r will be equal to, small r will be equal to nothing but our capital R. Therefore we can write that at center of sphere, the distance of any point on the ring to the center is capital R, because this ring to the center is always going to have a distance of our capital R. So we can say at the center of the sphere, the distance from any point on the ring to the center is capital R. Therefore we can say this small r will be equal to our capital R. And if you talk about the direction of the magnetic field, the direction of the magnetic field will be always perpendicular. So it will be somewhere like this. So this will be a dB. And this is current element somewhere here, that is about dl. And there will be another current element, suppose somewhere here, which will be also a dl, and whose magnetic field will be also in this direction. And if we divide that into two components, we can say the horizontal component are going to balance out each other. So only component that will be left will be the vertical component. So we can say that by symmetry, can write for each element on one side of the ring there is diametrically opposite element producing same vertical component but opposite horizontal component. In simplest term, we can say that this is the ring, this is the center. So this is small element, suppose dl1, and it will be producing a magnetic field which is somewhere here, that is db1. And the small element which is diametrically opposite, suppose this is dl2, obviously dl1 is equal to over dl2, okay, only for differentiation, and it will be producing a magnetic field which will be in this direction, db2. And if we divide it into the two components, so this angle is about theta, so this will be over db1x and this will be db2x. So this will be over db1y as well as db2y. So this db1x will be equal to db2x. So only component that we left in the vertical direction. Okay. And so angle is theta, and therefore you can say that so we are left with only our opposite horizontal component. Therefore from here we can say that the horizontal component cancels out. Horizontal component cancels out. Therefore, we can say that each element produces a magnetic field which is dB, and which will be equal to over mu naught 4 pi di times dl upon r square. And the vertical, because the angle of theta is with respect to our vertical is our theta. Okay. Therefore we can write that our length of the ring, which we already know is our length of ring, which is L, is nothing but our 2 pi and our r sine of theta. Therefore, we can write that our dB will be equal to our mu naught upon 4 pi, and current is our di, and the dl is going to give us our integration as our L divided by r square, and this will be our sine of theta. And we can substitute our di now, and as well as our L. Therefore, we get our magnetic field will be equal to mu naught upon 4 pi. This comes as charge density omega r square sine of theta d theta, and this comes as about 2 pi r sine of theta and our r square multiplied by sine of theta. So we get that the magnetic field will be equal to our mu naught 4 pi omega, and this is our 2 pi r sine cube theta and d theta. So this is our magnetic field because of one ring. Okay, now we are going to do it for our n number of rings and integrate it from theta 0 to pi. So you can say total magnetic field that is B is equal to our integral 0 to pi dB. So we get that our B will be equal to 1 by 2 our mu naught omega times r 0 to pi sine cube theta d theta, and we can easily compute this, and therefore we get that the value of magnetic field at the center will be equal to 2 by 3 mu naught charge density omega times r, and its direction will be along z unit vector. So these were the questions with respect to our magnetic field. Okay, especially in the last part, for the last question, we have to remember that we was supposed to find out the magnetic field of a sphere which is rotating about the axis which is along its diameter. So suppose we assume that this is our z-axis, and in order to solve this, suppose this is center, and we took a ring and which is at a r is the radius and angle is a theta, and it is rotating about the z-axis with angular omega. So for our ring, we assume that if dl is the current element, its width is dw, and the charge it is holding over dq. From here, we try to find out what will be the value of magnetic field at this point, which is supposed as our dB. And here we know that we have done it multiple times also. Suppose this is our ring, and we are going to find out magnetic field at this point. So for a current element, suppose here it is our dl1, there will be opposite diagrammatically current element, another one that is our dl2, And for the sake of simplicity, we can say this dl2 is equal to dl1. Therefore, the magnetic field, because of dl1, will be somewhere in this direction. Let us suppose this is our db1, and because of this dl2, it will be in this direction, that is our db2. And we can easily divide this into components. So these two components are going to balance out each other. So only magnetic field will be along our vertical direction. Okay. So this is the important part here. And similarly, this sphere can be divided into n number of components. Okay. Therefore, we got the value of the magnetic field dB because of our one ring which we considered. Okay. And then we integrate it with respect to for our entire, that is 0 to pi. This gives us the total magnetic field at the center of the sphere when it is rotating at a certain angular speed, that is our omega. Okay. So this was a little bit important part here in the last question. Okay. So this completes all the questions. Thank you.